Alright, let's talk about something huge. I mean truly massive. We're talking about those giant container ships and bulk carriers that move just about everything you own across the ocean. Ever wonder how they know how much stuff they've loaded on board? It's not like they can just pull onto a giant truck scale at a weigh station. The answer is surprisingly clever, and it all starts with a set of numbers painted right on the hull of the ship. These are called draft marks, or sometimes plimsoll lines, and they are the unsung heroes of global trade. They tell you exactly how deep the ship is sitting in the water, which, as you'll see, is the key to everything. These marks aren't just slapped on there with a can of paint, they're placed with incredible precision at 3 key locations on both sides of the ship. One set at the front, or the bow, one at the back, which is the stern, and one right in the middle, at midship. This gives you 6 points of reference in total. The numbers are big, usually in meters, so you can read them from a distance while standing on the dock or bobbing alongside in a small boat. They look a bit like a ruler, showing you exactly how many meters of the ship are submerged. It's a simple, rugged system that has to work in any port, in any weather, day or night. It's a dirty job, but a critical one. The whole idea is based on a principle that a smart old Greek guy named Archimedes figured out a long time ago. When you put an object in water, it pushes aside or displaces a certain amount of water. The weight of that displaced water is equal to the weight of the object. So, a heavier ship sinks lower and displaces more water. A lighter ship rides higher. The draft marks are the tool we use to measure that displacement with surprising accuracy. They turn the entire ocean into a massive floating scale. It's a brilliant low-tech solution to a very high-stakes problem. So, next time you're down by a port and see one of these steel behemoths, take a look at its side. You'll see those numbers, often a little weathered and stained by the sea, quietly doing their job. They are the first step in a fascinating process of measurement and calculation that ensures these ships are loaded safely, and that everyone, from the shipper to the buyer, knows exactly what's on board. It's a testament to the simple, effective ideas that keep our modern world running. It's not glamorous, but, without it, the whole system would grind to a halt. Now, just knowing how deep the ship is at one spot isn't enough. A ship rarely sits perfectly level in the water. It can be tilted forward or backward, a condition called trim. If it's heavier at the back, the stern draft will be deeper than the bow draft. This is where the ship surveyor comes in, a person whose job is to get this right. The surveyor, often from a small boat, has to read all 6 sets of draft marks. Media group, ship surveyor in small boat taking notes beside large cargo vessel draft marks. Marine surveyor using clipboard near ship hull at stock, at distribute equally. Forward, midship, and aft, on both the port, which is the left, and starboard, which is the right sides. It's a job that requires a good eye and a steady hand, especially when the water is a little choppy. Once the surveyor has all 6 readings, the math begins. They first average the readings on the port and starboard sides for each position. For example, they'll take the 2 forward readings and find the average to get the mean forward draft. They do the same for the midship and aft marks. This step corrects for any sideways tilt or list the ship might have. It's about finding the true centerline depth. This isn't just a quick glance, it requires careful observation, accounting for waves that can make the water level bob up and down against the hull markings. With the mean drafts for the bow, midship, and aft calculated, the surveyor then performs another calculation to find the ship's overall average draft. You might think you just average the 3 numbers, but it's a bit more sophisticated. The midship draft is given more importance in a special formula because it represents the widest, most voluminous part of the ship. The formula is typically media group, formula written on clipboard with ship in background, surveyor referencing calculation sheet beside ship hull at stock at distribute equally, forward draft plus aft draft plus 6 times the midship draft, divided by 8. This weighted average gives a much more accurate picture of how the entire vessel is sitting in the water, accounting for that forward and back trim. This whole process of reading marks and calculating averages is done twice. Media group, large cargo vessel at port, empty and then fully loaded side by side, time-lapse of ship being loaded at port at stock at distribute equally, once when the ship arrives at the port, relatively empty, and a second time after it's fully loaded. The difference between the initial or light draft and the final or loaded draft is what tells us how much the ship's displacement has changed. And that change, my friends, is caused by one thing: the cargo. We're getting closer to the final weight, but there are a few more crucial details to consider before we can stamp the paperwork and call it a day. So, we have the ship's average draft. Now we need to turn that measurement into a weight, a tonnage. This is where two more critical factors come into play: the density of the water and a very important book called the hydrostatic tables. First, let's talk about water. Not all water is created equal. Salt water is denser than fresh water because of all the dissolved salt in it. This means a ship will float higher in dense salt water than it will in less dense fresh water. Think of it like trying to float in the Great Salt Lake versus a swimming pool. You're much more buoyant in the saltier water. To account for this, the surveyor takes a sample of the water the ship is floating in. They use a special tool called a hydrometer to measure its exact density. This is a non-negotiable step. Getting the density wrong can throw the final weight calculation off by hundreds of tons, which can lead to big problems and costly disputes. Whether the ship is in a brackish estuary, a freshwater river port, or the salty open ocean, knowing the precise density of the water it's displacing is absolutely fundamental to getting an accurate result. It's another one of those small details that makes a huge difference. With the average draft and the water density in hand, the surveyor turns to the ship's hydrostatic tables. This document is like the ship's DNA, unique to that specific vessel and provided by the shipbuilders. It's a massive chart of numbers that tells you everything about the ship's characteristics at any given draft. The most important column for our purposes is the displacement column. The surveyor finds the ship's calculated average draft in the table, and right next to it is the corresponding displacement tonnage. This number represents the total weight of the ship and everything in it, assuming it's floating in standard seawater density, usually 1.025 kilograms per liter. But wait, what if the water density is different from the standard 1.025? The surveyor has to make a correction. There's a formula for that, of course. They adjust the displacement value from the tables to account for the actual density of the water they measured at the port. This corrected figure gives them the true displacement, the total weight of the ship and all its contents in its current environment. We now know the total weight of the floating giant. The job is almost done, but there's one final crucial step of subtraction to isolate the weight of the cargo itself. We have the total weight of the ship as it sits in the water, but the goal is to find the weight of the cargo, not the whole ship. So, the next logical step is to subtract everything that isn't cargo. This is what we call the deductibles, and it includes all the consumable items on board. Think of things like fuel oil, diesel oil, fresh water for the crew, ballast water used for stability, and various stores like lubricating oil and provisions. The weight of every one of these items must be accounted for and subtracted from the total displacement we just calculated. To do this, the surveyor, usually with the ship's chief officer, goes through the ship's records. They check the levels in all the tanks, fuel tanks, water tanks, ballast tanks, and use the ship's calibration tables for those tanks to determine the exact weight of the liquids inside. It's a detailed inventory. They're not just guessing, they are measuring and calculating precisely how many tons of fuel, water, and other fluids are on the vessel. This is done for both the initial survey before loading and the final survey after loading, because these amounts can change while the ship is in port. Beyond the consumables, there's one more sneaky item to account for: the ship's constant. This isn't something you can easily measure on the day. The constant represents the combined weight of everything that is part of the ship, but not included in its official lightweight, which is the weight of the empty vessel. This includes the crew and their effects, the spare parts, the tools in the workshop, the paint in the storeroom, and even the accumulated mud and muck in the ballast tanks. The ship's constant is an established figure determined from the ship's history of draft surveys, and it's also subtracted from the total. Finally, we have all the pieces. The surveyor takes the final displacement from the loaded draft, subtracts the initial displacement from the light draft, and then adjusts for any changes in fuel, water, and ballast between the two surveys. The result of this grand calculation is the net weight of the cargo loaded. This method, the draft survey, is a brilliant and universally accepted way to weigh something that can't be weighed. It relies on physics, careful measurement, and meticulous record-keeping. It's a dirty job, sure, but it's the honest, hard work that keeps the world's cargo moving accurately and safely.